Alright, so in this lecture we want to talk about the basics of cosmology. And the basics of cosmology are of course the observations which drive the interpretation of the data. First data which we want to look at is the night sky. Night sky is dark, as we all know. In a starry, clear night you can go outside, you see beautiful stars. However, in between the stars there's pitch darkness. And that's kind of a surprising feature because that's something that already Olbers realized centuries ago. In an eternal and infinite universe, basically every line of sight that you would look to would be basically pointing at some point to a star, if the universe is infinite and also eternal, and the stars are also eternal. And the fact that basically the night sky is dark basically means that the universe has to be finite. So first thing, dark night sky, also commonly known as Olbers paradoxon, implies a finite universe. Second observation that I want to discuss briefly is the fact that if you look at the abundance of the chemical elements in the universe, it's kind of a surprising observation that people, when people first observed spectra of other stars, that the abundance of, for example, helium is about the same. And this implies that since helium seems to be abundant in about the same quantity overall, that this might hint towards a common origin. But where would that common origin come from? Because supposedly the stars generate all the helium, then basically it would depend upon where you look, what's the history behind this, how many generations of stars have been processing helium, that this is something which you usually would not consider to be the same everywhere, given that also we know that the metallicity, that is the stuff which is heavier than helium in the stars, varies a lot. However, the helium abundance remains rather constant. And the mass ratio which is usually measured, this so-called YP, is about the order of 0.25 and slightly above, so 0.25 and maybe up to 0.28, that's the solar helium abundance. That means that there must be some universal origin of helium. And that's kind of puzzling because there's no clear way to understand this unless you assume that this was all generated during an early hot universe where the density and temperatures were such that helium could be generated out of the primordial hydrogen and would form at the abundance that we see today everywhere in the universe. Now the next observation that's been coming up shortly after realizing that the helium abundance is more or less constant everywhere is the fact that the universe seems to be expanding. So that's the so-called Hubble expansion that we observe. So Hubble realized that he was looking at the spectra of objects that he could measure the distance of, that there seemed to be a common pattern, that is, the objects which have an apparent receding velocity are also the ones which are further away. And an explanation for this is that the universe is expanding. So Hubble's law basically can be explained by an expansion. The next one is the thermal background radiation, which is really the breakthrough result, which we will discuss at length. And that is basically telling us that after all there is some light in the sky. So the night sky is only apparently dark because we are looking with our eyes, which are limited to the visual. However, if you look at frequencies of about 150 gigahertz, then you basically realize that we are looking at light coming from everywhere, and it has always the same property. It is a thermal radiation field of a temperature of about 3 Kelvin. And that again makes us realize that there must be some kind of hot state which the universe had in the past, out of which, for example, we can still see this thermal emission shining towards us. And this is basically now the cornerstone of the modern cosmology, which is this concordance model in which we assume that the universe consists out of different materials, among which we have frustratingly the dark energy and dark matter, which we still don't understand. And now the final observation, which is of cosmological relevance, even though it does not really relate to the early universe in a direct way, is the way that structure has basically been forming. So the structure that we observe today, that means that's not the early universe anymore, but that's more or less the universe that we see today has evolved out of something which was forming already earlier, and the way that the structure is formed basically gives us a way to trace back to the development of matter densities in the early universe. And so that's a field which has been rapidly evolving and basically also driven by new instrumental inventions and also new instruments which basically, or data analysis capabilities in the framework of big data. Now, since all of this seems to be pointing towards a hot and expanding universe, let's go through the basics of how we want to describe that in a more quantitative way. So I don't want to make this too technical, but I just want to point out that we basically need a metric which tells us how we can measure distances in this universe, and that's the so-called Robertson-Walker metric. In which the distance squared between 2 points is basically measured in a 4-dimensional space-time. So we have a time component and a spatial component. And the spatial component basically gets rescaled with a universal scaling factor. We call that A, and that's a time-dependent function. It's just a number, essentially, which evolves with time. And then we have spatial distances as measured in comoving coordinate system. So we have an R, which is sort of the spatial component, and then we have, or the radial component, and we have minus kr squared, where k is a number which indicates the curvature of the system, and it has to have the units of 1 over distance squared, otherwise you don't get this unitless number down here. And then we have also the component which comes from the angular displacement. So this is basically a full set of coordinates that we're talking about, and this scale factor A is a function of t, and it basically tells us how to scale the coordinate system that we have at any given time in our system. So a spatial coordinate system would be basically then rescaled at a later time with a scaling factor to take into account the expansion of the universe. So A is a monotonically rising function usually of time, and basically R would be then, R and also the angles that go with it would be part of the comoving coordinate system, the spatial comoving coordinate system. And the K is in this sense a measure of the curvature, and because it's kind of difficult to understand curvature in a 3-dimensional spatial coordinate system, I just want to pull in here a figure which gives you a little bit of a visualization how curvature would affect, let's say, a 2-dimensional plane in a 3-dimensional spatial coordinate system. So zero curvature in the middle basically shows you what the flat metric flat system would look like with k equals 0. In which then, if you have 2 beams, they would be parallel all the time. They would never cross, of course, and they would not diverge. And if you draw a triangle in this coordinate system or in this flat spatial geometry, you would end up with the sum of the angles to be always 180 degrees. If you have a positive curvature, so in this case particular, it's would be k equals 1. So generally it would be larger than 1, but let's say k equals 1 in this way. You would have a sphere embedded in like a 3-dimensional sphere. Here now in this case is depicted by a 2-dimensional surface which is closed, and you would then have 2 rays which would go parallel. They would eventually meet, and if you draw a triangle again and calculate the sum of the angles, you would end up with an angle which is larger than 180 degrees. And for the negative curvature here, it's like a hyperboloid surface drawn. You would have 2 rays running parallel, they would diverge eventually, and the sum of the angles in a triangle would be smaller than 180 degrees. Now let's talk a little bit about the scale factor, how that works. Imagine you have a coordinate system drawn in your comoving system, and you look at it, how it evolves over time. What would basically happen is that the coordinate system is like a grid that you could draw on your surface, and that would expand away. However, the actual values that you would assign a point in that grid would remain the same because the comoving coordinate system doesn't change in time. The actual change then is just a rescaling of this coordinate by scaling factor A. Now let's have a look at how this could affect, for example, velocities. So let's assume we have now something, we call this the physical value of r, which is then a function of t, which is the scaling factor times the comoving coordinate system. Now let's assume we calculate the time derivative of this part here. So that would be then the r dot as the time derivative of this physical coordinate. and then we just apply the product rule. So we would have A dot times R plus A times R dot. And instead of writing R, we can just rewrite R phys. So that would be A dot times times R phys, physical distance, divided by A, plus, and instead of writing A times R dot, this would be essentially a peculiar velocity. So we call this V pec, so to say that this is something which is moving in the comoving frame by itself. We call it a peculiar velocity. And so A dot over A, we put that together as the Hubble constant. We call this H times R phys plus peculiar velocity, where A is defined as the ratio of A dot over A. So that's like a fractional variation of the scale factor. And if we now want to apply this to, for example, the measurement of a wavelength, we can derive an important relation, or we can recover an important relation, which is the Hubble law. Let's have a look at what we call redshift. That's usually called Z, and that's defined as the wavelength that we observe minus the wavelength at emission divided by the wavelength of emission. So lambda 0 is the wavelength we observe, and lambda 1 is the wavelength at the time of emission. So that's called redshift, and often enough also redshift is measured in units of, or redshift relates to the velocity, because in principle it is a similar effect as the Doppler shift. However, it is not a Doppler shift that we observe cosmologically, because it relates actually to the change of the scale factor. And let's have a look at how that actually works. So the scale factor changes the wavelength. So when we observe lambda 0, that is proportional to lambda 1, and it's scaled by the ratio of the scale factor of today, or of the observer, divided by the scale factor at emission. And so if we put that in, usually A0 would be larger than A1, so lambda 0 would be then larger than lambda 1. So the wavelength gets stretched out, and therefore we observe something like a redshift, as it's called. Now, if we change this and we plug it in here, over there, then we can see that redshift equals A0 divided by A1. And then basically we have lambda 1 here, minus lambda 1 divided by lambda 1. And then we can pull out the lambda 1 or everywhere, and then we get basically this is A0 over A1 minus 1. And that means that redshift, and redshift plus 1 equals A0 over A1. So that means that, for example, if we observe a redshift of 1.5, then this means that the ratio of A0 and A1 would be 2.5. That means that there's a factor of 2.5 in the scaling factor between A1 and A0. So that's quite a lot. So that means that expansion really is an important effect that we have to consider. Now, if we consider that we are looking at small changes of the scale factor, small means that basically we have to constrain ourselves to something like T1 minus T0 minus T1. So the time difference between the time at observation minus the time of the emission times H0, and H0 is then the Hubble constant as today. If that is a small number, then we can write A1 or A0 to be A1 times 1 plus T0 minus T1 times H0. So that basically is like a series expansion. So this is true only if this is valid, this condition. And then there would be higher order terms in it, where we have a higher order of this T0 minus T1 times H0. And then basically we can rewrite this as that we bring over A0 minus A1, divide this, so it's A0 divided by A1, equals 1 plus T0 minus T1 times H0. So that means redshift is proportional to the time difference between emission and today, and that is the light travel time. So essentially we can also rewrite that in terms of the distance. So z equals, if you want to write that with distance, then we would have to say this is distance divided by c times h0. Means that is proportional to distance. And that's Hubble's law, which we just have recovered here. So Edwin Hubble was measuring systematically objects, trying to determine the absolute distance, and he was using the relation between magnitude or luminosity of stars which are pulsating, so-called Cepheids, and the apparent magnitude allowed him then to measure the distance modulus and therefore the distance to the objects. And then he was correlating that with the measurement of the redshift of lines that he would detect. And this in the end led to his proposed Hubble Law. However, actually he was measuring, his measurements were constrained to very nearby objects, and the actual local flow, that is the velocity implied by gravitational interaction with neighboring objects, has been biasing of his observations. But we have confirmed the general principle in various measurements, and I just want to show you here how basically this kind of correlation looks like. And I plot here the values of redshift on the y-axis. So that's going from 0 to 0.1. So that means that the fractional change of the wavelength is 10%. And on the other hand, you plot here the distance in megaparsecs, where the distance must be obtained with some way of determining the distance. Once you've confirmed and understood the Hubble law, you can in turn use the redshift measurement to determine the distance. But in order to measure the Hubble constant, that is the h0, you need to somehow measure the distance independently. And this requires careful measurement using the distance ladder. That is, you start out with nearby distances using parallax measurements, and then you work your way up to more and more distant objects. And that can be kind of tricky. And there's also some ongoing controversy. That is, if you now draw a line through this plot, you get the slope, and that slope is essentially telling you the Hubble constant. So that's here 72 kilometers per second, 72 kilometers per second per megaparsec. So that's the value of h0. That would be 72 kilometers per second per megaparsec. And if you take out the distances here, then you basically see the Hubble constant is just an inverse time unit. So it's like a rate, expansion rate. Anyway, so that value is preferred by the measurements relying upon direct estimates of distances using the distance ladder. However, you can also determine the Hubble constant from, for example, the measurement of the CMB, and that turns to be out systematically lower. And there's quite a dispute about this discrepancy. Some of it may be related to systematics, but it's statistically speaking significant enough to worry a little bit about the fact that a local measurement of the Hubble constant does not match the Hubble constant as you get it from the CMB measurement. Anyway, so the Hubble constant basically is something which, or the Hubble's law can be recovered, but keep in mind the Hubble law is only valid for this kind of relation, that is, you have to confine this to small distances. So in this case, as I said, redshift of 0.1 means that the value of h0 of 8.1 is basically 1.1. So the universe has been expanded only by 10%. So that means that this fractional change here is still small, so that's still okay. Otherwise, this curve starts to deviate from a linear law, as you will see also a little bit later. Now, in the end, basically, when we want to talk cosmologically, what is the content of the universe, let's do a quick breakdown of the constituents, or let's say the composition of the universe. And this is, of course, now a very rough breakdown, so I'm not going to be discussing too much components which are again, some you would like to make a distinction between dust and plasma and so on and so forth. But I just want to make this situation rather simple in a sense that I want to distinguish between non-relativistic forms of matter. That is matter which is having most of its energy simply in its rest mass, and kinetic energy small with respect to its rest mass energy. And this is something which is often called cosmic dust, because it doesn't have pressure attached to it. It basically has no relativistic component, or it is non-relativistic. And the second form that we want to distinguish here is relativistic matter. And that is then, for example, forms of radiation, and we often call this simply radiation, even though, strictly speaking, for example, neutrinos fall into the same category. They are mostly relativistic, and they are still not radiation. They have a non-zero rest mass, but it's small against the kinetic energy. So that's usually called then radiation. And we call this then the energy density rho mass or rho matter. This we call rho r for radiation. And then we have a third form which is very enigmatic, and that's the vacuum energy. And this is somehow a tricky thing, because we still don't know what it is. We only know that it has the property, the characteristics, that it behaves almost like a 0-point energy. Often it's called rho lambda because it is also related to cosmological constant. And in principle, you could interpret this in a sense that this would be also the 0-point energy of the fields present in the universe. So this would be in principle a huge number, because the 0-point energy is large. We usually completely neglect it, but it's certainly much larger than what we measure today as the cosmological constant. So now let's think about how these quantities scale with the scale factor. So if we think about cosmic dust, the situation is quite simple, because cosmic dust is similar to like particles, which move slowly, and when the universe expands, the number of particles per comoving volume element is conserved, and that means that the number of particles per physical volume element has to scale with a to the minus 3. Now for the radiation, the same thing holds true in a sense that if we assume that radiation is not interacting, it's not basically annihilating, it's not producing matter, or it's not being fed by matter, antimatter self-annihilation or annihilation processes, then basically the radiation is like an adiabatically expanding gas in the universe, it's called a photon gas, and therefore the number is conserved, similar as the entropy density as a matter of fact. So the number density in co-moving coordinate system is conserved. So that would be like a to the minus 3 in the physical quantity. But since we deal with energy density, we also have to take into account that the energy is reduced through the expansion. As we saw, the wavelength gets stretched, and therefore this energy density goes with a to the minus 4. Now finally, the cosmological constant is at least behaving to the observations that are possible. It's behaving like a cosmological constant, and therefore the energy density remains constant, independent of whether you consider the physical or the co-moving volume. It doesn't matter. So this one is basically just a constant under the expansion. And having said all of that, we can basically proceed to write down the important equation which explains, or which is the one which describes the universe expansion. And this so-called Friedmann-Lemaitre equations, however, rely upon two assumptions. And the two assumptions are often called the Cosmological Principle. And they basically state that the universe is isotropic and homogeneous for, let's say, a sufficiently large scale. So clearly, our universe as we observe it today in our near environment is neither isotropic nor homogeneous, but on sufficiently large scales, observations tell us that the universe actually is isotropic and homogeneous. And this means that essentially two observers would observe pretty much the same isotropic universe. So the other way of phrasing the cosmological principles is universe is independent of the observer, looks the same. And that's an important assumption, and it is verified with observations to some extent, at least, that you can see that the universe becomes isotropic and homogeneous on sufficiently large scales. And that brings me to the so-called Friedmann-Lemaitre equations, which you can derive from general relativity equations, where once you can apply the cosmological principles, you know that the Ricci tensor basically has to be proportional to your metric, which is given by the Robertson-Walker metric, and then you have a simple solution for the scale factor, which you can write down. So it's often written in a way that I write here h squared. That's the a dot over a squared expansion rate, is given by a prefactor here 8 pi g over 3 rho, and rho is the energy density in the system, minus k over a squared, where k is the curvature term that we had before. And if we assume that the universe, for example, if we, let's say, think about what density is required to make the universe flat for today, we can basically say, let's assume k equals 0, and what's the density that basically leads to this? Now we can just rewrite this equation in a way that we say critical density is equal to 3 over 8 pi g h0 squared, because we just basically take out that last term when it's flat universe, and then we have a critical energy density which makes the universe behave like a flat universe today. And then basically we can turn that into a number. So basically now I don't write the energy density, but just write the equivalent, and then we get something like 1.1 times 10 to the minus 5 proton rest mass per cubic centimeter. And that's a very tiny number. Comparing that, for example, to the density in the interstellar medium in our galaxy, that value is about 1 proton per cubic centimeter. And however, if you look over the large scale, this is the average critical density that you would require over a large scale. That basically tells us that the universe is basically very, very, very dilute in comparison to what we see already as a very dilute gas in our interstellar medium. I should add here there's an h0 missing, h0 squared, and that quantity h0 is basically a unit free number that scale that we use to write down the Hubble constant. So h0 is h0, small h0, times 100 kilometers per second over megaparsec. So this way we can basically carry through the scaled value of the Hubble constant, and it appears in the equations in such a way which makes it convenient to recalculate the critical energy density depending upon the choice of Hubble constant that I'm using. Now we can now basically, we have now a pretty good picture of the universe in a sense that we understand how expansion goes. We can rewrite that thing a little bit better because we can take this rho and we break it down to be essentially the matter and the radiation and the cosmological constant, which contribute. And then there's a convenient way to rewrite the equations by rescaling this energy density towards a unit-free number, and that's then essentially rescaling it to the critical density. So we basically say for any component I, it could be the matter, radiation, or the cosmological constant, we rescale this should be omega, and we call this omega I, that's rho I over rho critical. And I should say this is rho critical 0, so that means that is the critical density as it is today for an observer at A0. And this basically can be then used. We can also rewrite the curvature in a similar way. So we define curvature in terms of critical density to be minus k divided by A0 squared H0 squared. And I should call these quantities 0 because they are referring to today's value. Often enough later on I will drop this, and then I will always refer to today's value because these are the ones that we measure. And then I will always point out that if we talk about something which is, for example, happening at a given epoch. So anyway, so this way we can rewrite the Friedmann-Lemaitre equations. So let me just call these so that you know what I'm talking about. So these are the Friedmann-Lemaitre, or this is the Friedmann-Lemaitre equation. And that basically says h squared equals h0 squared times omega rho 0 a to the minus 4, and then you find again these kind of scaling relations of the densities as I was indicating them before, but now they're simply normalized to the density today scaled to the critical density. So I should write this maybe like this. Plus omega matter at a0, a to the minus 3, plus omega k0 times a to the minus 2, plus omega lambda 0, and that's as it is today. And now this is basically bringing down all of cosmology that relates to the dynamics of it to a handful of parameters. So we have the energy densities and the various constituents, and many of them are very precisely known. So let me just write them down here for you. We will find out how they are observed in more detail in the next lecture. But we know that the omega R0, that's the radiation energy as it is today, is very precisely known. I don't quote the errors here, but it's smaller. I give it at least to one significant digit here. So that's 9.4 times 10 to the minus 5 in terms of critical density. So it's a very small component today. Rho meta 0 is today as 0.32, and omega lambda 0 is 0.68. And the curvature component is smaller, equal to 0.01. So we'll talk about this at a later section, how this is derived. We also discuss the uncertainties, but it gives you now a very good breakdown of how the different densities are today, which means basically they all of them sum up to be 1, very close to 1, which means that curvature is negligible. The universe essentially, for all that matters, it's flat. Secondly, we see that matter density is subdominant and we are dominated by the vacuum energy, and radiation doesn't matter so much. But this is as it is today. However, you can use the Friedmann-Lemaitre equations now, or you can use the scaling relation to scale these terms back to the time in the past. So we can trace out the history quite easily. And let me just pull in a plot for that here. So we can plot here now the 3 components. So this is the matter. So this goes with a to the minus 3. And you plot this here now, or we plot this here as a function of the scale factor. That's essentially today. So A0 is set to be 1. That's the convention. So scale factor is today is 1. And then you go back in the past and you see that this is rising with a to the minus 3. Radiation goes with a to the minus 4. So even though today it is subdominant by a few orders of magnitude, there is a time in the past over here where the radiation dominates over the matter, and here matter dominates over radiation. So this is basically a very important time that we will visit again, and we will talk about it a little bit more. So this is basically matter. This epoch is the epoch of matter radiation equality, and in this case you've got a radiation dominated universe before that time, or before that with smaller scale factors, and at later times you find a matter dominated universe. And we're today not even in a matter dominated universe, because if you look very carefully, the cosmological constant, which is constant as the name implies, is basically now dominating. So now we basically, from this point onwards, which was just in the recent past, we can say that omega lambda is larger than, or let me write this in rho lambda. Rho lambda is larger than a rho matter, okay? And right now it's about 2.5 times larger. So if we now want to look about, we know the past, we can think about the future of this system. Or maybe I should point out, I want to show one more plot here at this point, which is kind of a bit more busy. but still something of importance because this gives you an idea of what we're talking about. So here's a nice plot which is showing you the evolution again of the densities in a slightly different way, but again, this is the same number here, so this is basically the scale factor a that we were looking at. So this is basically a as a function of t. And now you see here a number of graphs. On the left side you see something which is related to the temperature, and the temperature basically has today some value, and if you go back in time or use smaller scale factors, the temperature rises. And so I did not discuss so far how temperature behaves with the scale factor, but let's talk about that for a moment here. So temperature basically is something which we know that there is a equation of state, for example, under adiabatic expansion. And the assumption we want to put here is that the expansion of the universe is essentially adiabatic by nature. So that means that the radiation field, while it expands, is carrying, is not changing its heat. Or there's no heat exchange, so dq is 0. As a matter of fact, also the entropy doesn't change, the entropy per volume, because the photon field is expanding in a way that you basically maintain the number of photons per volume, and the temperature, the number of photons basically is a measurement of the entropy of the system. So temperature then, therefore, scales. How does it scale with the scale factor? Let's talk about that for a moment. So for the photon gas, we know that we can write down a adiabatic law. So let's assume that there's no heat exchange, so delta Q equals 0. We look at it whether this is a valid assumption or not. And then we can say that volume times adiabatic coefficient kappa minus 1 times T is a constant. And kappa is the adiabatic coefficient. For a relativistic gas, that is a photon gas, for example, we can write this down, kappa to be 4/3. I cannot explain the details why this is like that, but essentially, you remember this is 5/3 for example, an ideal monatomic gas. And for a photonic gas, it turns out to be 4/3. It's slightly smaller than this. And that means that we can rewrite T to be proportional to V to the, then we would write 1 minus kappa, so that would be V to the minus 1/3. And V to the minus 1/3 is just the inverse of the scale factor. So that means that T scales with 1 over A for photonic gas. For a matter gas, for example, this actually scales different. It would scale then with 5/3, and then you would get that it goes with A to the minus 2. T goes with V to the minus 2/3, and that's essentially A to the minus 2. But we are not concerned so much about the temperature of the matter, because as it turns out, photons are so much more overabundant that they are the ones which are driving the equilibrium system. So that's where the temperature comes from to start with. Now there's an interesting story that I just wanted to highlight here briefly. That is that if you now plot the temperature as a function of time, you basically see this is the temperature today, and it's at a value which is about 3 Kelvin. Now if you go back to a scale factor of about 10 to the minus 6, for example, then basically the temperature would go down by 6 orders of magnitude. So you would end up something like 3 times 10 to the 6. And so the temperature increases the further you go back in time. And this is true for the adiabatic case. And you see there's a little bit of a deviation here at a scale factor of about 10 to the minus 9. And that is a time when basically you had the electrons annihilate. Electrons and positrons would annihilate, and therefore neutrinos who would be interacting with the electrons would decouple from the system shortly after that annihilation. And that basically means that at the time when basically electrons and positrons would be annihilating, this would lead to a slight increase of temperature in the photons because they would heat up the photons. And that's basically the time when we basically have no, so this is adiabatic here. And then here we have some heating process taking place. And before that is essentially again adiabatic. And you see the temperature change is very, very small. And that has to do with the fact that photons are so much more overabundant than the electrons, positrons, that it doesn't really matter that all of the electrons, positrons annihilate. And so therefore, whatever happens in the universe, photons are so much more abundant that they drive the thermodynamic system. Okay, and maybe I just go back now to this simpler plot here, because there's one more thing which we can basically learn from this, is that we can have a look again at what will happen in the future. So you can also look to the right of the figure now at scale factors which are sort of in the future from now and how the universe will behave. And as I said, the dynamics of the system are described by the Friedmann-Lemaitre equations. And one of the things that we learn from this is that the universe seems to be rather flat in a sense that there's no additional curvature in the universe. However, we can also look at how the scale factor will behave in the future. Because the scale factor, the dynamics of the scale factor, we can take this from the Friedmann-Lemaitre equations, and we can scale this or we can solve this for the future depending upon how the constituents are. So this is a way of plotting this. So here we now plot the omega lambda. So that's essentially the cosmological constant value and the matter density here. Now in a flat universe where k equals 0, any universe would fall along that red dashed line here. Okay, so as it turns out, since we are living in a flat universe, we are at this point over here. So omega lambda is about 0.68 and matter is about 0.32. Okay, so round about here, that's our universe, how it is. And now, if you think about what kind of future does the universe have in this kind of scenario, you see that everything which is falling in this green regime will be an accelerating universe. And it's also a universe where basically you can go back to the past and you find that the universe will be having a singular state, that is that the scale factor will go to 0. And this is something which I did not describe here before, but in the way that the universe behaves, the scale factor would start at a value of 0 for t equals 0. And that's what we call the hot Big Bang scenario. So anything which is here has got a Big Bang, and it is also accelerating in the sense that since the cosmological constant is the one which is there, it drives the dynamics of the system. And if it turns out, if you take the Friedmann-Lemaitre equation, and you basically look at the Friedmann-Lemaitre equation, assuming that all of these other parameters are essentially 0, you essentially get a solution where you basically have something which is exponentially growing. So that's what's called acceleration. So the scale factor will grow exponentially in this scenario, and that means that even though we're today at a universe which is only slightly accelerating, but the acceleration will pick up, so the slope will increase. And so if you were, for example, at a value which is sort of falling in the orange regime, you would have not a singularity, you would have sort of a bounce in the past. So at a finite scale factor, the universe would be contracting until then and then would be expanding. If you're sitting in a parameter space, which is this blue part, you would have a decelerating universe. That is basically, it would turn down, but it would still continue expanding. So it would basically go at some point and just stay asymptotically in a constant value of the scale factor. And if you are below that line, sort of in this magenta type shaped colored regime, you would live in a collapsing universe. That's a universe where you basically would have a contraction. So that's basically our scenario. And if we now go back to this figure here, we can already discuss briefly what will happen in the early universe. You can imagine that the temperature will go up, and at the temperatures which are, for example, then giving you the average energy of the constituents of the universe in thermal equilibrium, all kinds of interesting things can happen. So at energies which are at the level of MeV, and that would be sort of 10 to the 9 or so, you expect that things would happen that are usually expected for nuclear physics. If you go to even smaller scale factors, even higher temperatures, you can imagine that, for example, things will happen which are relating to the weak energy scale. and that could happen that are relating to the QCD energy scale, and even to energy scales relating to physics we haven't explored with accelerators yet. And all of these things will happen in an expanding universe, and that's an interesting story to follow up on. And you can basically now understand that if you see such an overview picture here, let me just pull that in for you. These kind of overview pictures are often shown where you have the cosmic age going from the bottom or up, for example, and you see that we are sitting now in a universe which is basically consisting out of galaxies and so on and so forth, but they must have formed in the past, so there's an area when these galaxies formed first, and this requires that there must be atoms, and the atoms were formed about at an age of the universe of 300,000 years. That's when this cosmic microwave background was produced. And before that you had nuclei and electrons freely roaming around, and even the nuclei were formed at some point, and this happens about 3 minutes after the singularity. And then you can go further and further and further in the past, when basically you go from the nuclei to the particles, and then basically at some point you go beyond the energy scale that is explored and has been understood in terms of our physical model, and then you expect some kind of all kinds of strange stuff happening, and ultimately we approach then the singularity, where we basically expect, for example, some kind of unification of the various forces happening. So the next thing we're going to be looking at is this area at about 3 minutes, that is the era of nucleosynthesis.